two sets of trajectories starting from nearly identical points. Within seconds, they've completely diverged. This is the butterfly effect, the heart of chaos theory, visualized in real time. And today, we're going to build this from scratch using only C++. In 1963, Edward Lorenz, a meteorologist, was trying to model atmospheric convection. He ended up with these three innocent-looking differential equations. The variables x, y, z represent the state of the system. The parameters sigma, r, h, o, and beta control its behavior. Lorenz discovered that certain values like sigma equals 10, rho equals 28, beta equals 8 over 3 leads to the system becoming chaotic. The trajectory never repeats, never settles down, and is incredibly sensitive to initial conditions. That sensitivity, in essence, is the butterfly effect, as a tiny change now leads to huge differences later. Today, we'll simulate hundreds to thousands of these trajectories and watch them evolve over time. For the graphics library, we will be using SFML, as it's something I'm familiar with, and also it's quicker to get graphics up and running without the OpenGL struggles. For now, let's just create a blank window. This gives us a full-screen black canvas. Nothing exciting yet, but it's our foundation. We need 3D and 2D point types. Let's keep it simple and make struct vectors containing 3 values, x, y, and z, for both floating point and unsigned integer types. Now, to see anything, we need to project 3D coordinates onto the 2D screen. There are a few techniques to do this. However, for simplicity, we will use orthographic projection, which is actually a technical drawing method. However, we can extend it to be used in graphics programming. For further simplicity, let's also ignore perspective for now. This gives us a function that takes in a 3D point and returns a 2D projection of this point. We will also need to account for the window's size to know where exactly to project this point to. Let's now test this by attempting to project a 3D cube onto our 2D screen. You may notice that I have gotten rid of our custom vector types and am instead using SFML's built-in vector types for better compatibility. The code generates a simple cube that is projected on the screen as a square which is viewed from one side. Right now, without changing the perspective, it does not look very impressive. Let's now shift our focus back to the Lorenz equations. We can view these equations as a single function that takes in a 3D point along with values for sigma, rho, and beta, and returns the derivative of this 3D point with respect to time. This can be easily written in code as so. These equations give us the positional component's derivatives with respect to time. However, integrating these equations analytically are not possible as they are nonlinear. So we will need to use a numerical method. Simple numerical integration methods like the Euler method are generally avoided as this system is too chaotic and results in a high amount of errors. The standard choice for performance and accuracy is the fourth-order Runge-Kutta method, which is what we will be using. The code implementation for the method is straightforward. It takes in a 3D point, calculates the positional component's derivatives with respect to time, and then integrates using the fourth-order Runge-Kutta formula to get the new x, y, and z values. We can visualize these positional updates by simulating a single circle using the standard chaotic parameter values for sigma, rho, and beta, along with a small delta time value for somewhat smooth motion. We can see that the behavior is indeed the chaotic movement we expect. However, notice how this point is already tracing out the famous butterfly figure you saw at the beginning of this video. One trajectory is interesting, but let's make this more interesting. We will create 200 circles with small differences in their starting positions using a uniform real distribution. This will cause the circles to appear as though they are one circle in the beginning, and then over time will separate into distinct trajectories following the butterfly shape. We will also use a larger delta time to visualize this separation more easily. Many circles, all the same circle, will make it challenging to differentiate between circles. So we will make each circle have its own color based on its index. There is a method to change these color hues into RGB values so we can set the color correctly for our circles. There are many resources online showing how to code this conversion, but this is the implementation we will be using. Now, let's observe how our circles with small differences appear to be one single circle. But after a few seconds, chaos emerges and a rainbow of colors trace out the butterfly shape. Points alone don't show direction or speed. We want trails, a fading line behind each point. We will store the last 400 points per trajectory in a vector representing the trails. Each frame, the old point will be appended to this circle's trajectory vector. Then, when drawing the trails, we will use ramping opacity values for the color to create a fading effect. Looking at this spectacle from one angle gets a bit boring. We created the 3D to 2D projection. For a reason now, let's make use of it. We will start by creating a camera struct, with distance representing a zoom value for our camera, azimuth, which is the horizontal rotation angle around the y-axis in radians, and elevation, representing the vertical rotation angle around the x-axis in radians. The default values for these don't matter too much since they will be changing as we drag the mouse. The rotate function simply adds a delta to the azimuth and elevation. However, note that the azimuth is wrapped to remain in the range of 0 to 2 pi, as this represents the possible rotation values from 0 to 360 degrees. The elevation is also clamped to avoid certain views, like straight up and straight down, whereas horizontal axis is unknown. The zoom function is extremely simple and just adds a delta to our view distance from the trajectory. The value is also clamped to prevent being too close or too far. The project function has been modified to accommodate our new camera perspective. The center of the scene has a Z value shifted by 0.25. This is to center the butterfly shape relative to our camera and was chosen through some experimentation. The rotation formulas for X and Y are equivalent to the standard 3x3 rotation matrices for X and Y values. Putting everything together, we can create a new perspective and 2D projection for our point using a camera, coordinates to pixels mapping with constants that were also found through experimentation. Using our new camera, we can visualize our simulation in 3D by clicking and dragging our mouse in different directions. This gives us a better understanding of the trajectories that lead to the butterfly shape. Now let's get to the moment we've been building toward. We'll create a second set of trajectories identical to the first, but with a tiny perturbation. Say add 0.01 to the x coordinate. Then we draw one set in cyan and the other in orange. At the start, they overlap. But watch what happens. This is the butterfly effect in real time. A difference of 0.01 leads to completely independent paths within seconds. It's not just a metaphor, it's mathematics. What started as a blank window became a window into chaos. We've built an interactive Lorenz attractor, explored the butterfly effect, and learned about differential equations, numerical integration, 3D projection, and real-time graphics along the way. I hope you enjoyed this journey as much as I did. Thanks for watching, and remember, even a tiny change can lead to a completely different outcome.